All right, so today we're going to talk about the derivatives of inverse trig functions. And what we're going to do when we talk about this is really talk about how do I get the derivative of a function that's kind of written in this inverse notation. And in order to do it, what we end up doing is implicit differentiation. Now, this is another one of those days where, kind of like with trig derivatives, I'm going to show you where the derivative comes from, but really at the end of the day, you just need to memorize the box on the bottom. So I'll be honest, memorize the box on the bottom and you're good to go, but you really should know how to get there. So if I want to take the derivative of y equals inverse tan x using implicit differentiation, what I'm going to do first is I'm going to say, well, y equals inverse tan x is the same as x equals normal tan of y. So basically I swapped x and y and swapped out the inverse, so that's fine. And now I'm going to take the derivative using normal methods here. So d dx of both sides, and the derivative of x with respect to x is 1, and the derivative of tan y with respect to x is a chain rule. I'm going to take the derivative of the outside, keep the inside, times the derivative of the inside. And then if I solve for dy dx, I'm going to get dy dx equals 1 over secant squared y. Now you can write that as 1 over you can write that as cosine squared y if you want, but it actually doesn't help us because we're going to do something else now. This says dy dx is 1 over secant squared y, but I really want this. This is a function. I really want my derivative to have x's in it. I want it to start as a function of x and have a derivative that's a function of x. So we're going to do a little trig magic here. Do you remember those trig identities where sine squared theta plus cos squared theta equals 1? And then if I divide everything by cos squared, I get tan squared theta plus 1 equals secant squared theta? Remember those? Sound a little familiar? Well, secant squared y can be rewritten as 1 over tan squared y plus 1. Secant squared is tan squared plus 1. Okay, well, why would you want to do that, Mrs. Weber? Well, because tan of y is right here. So tan squared y would be x squared. And lo and behold, the derivative of inverse tan x is 1 over x squared plus 1. Wow, that comes out of left field, doesn't it? The derivative of inverse trig is a rational expression? That's weird. Well, it's weird, but it's true. That is the derivative of inverse tan. We're going to do the same process for the derivative of inverse sine using implicit differentiation. So I'm going to rewrite it as x equals normal sine of y. I'm going to take the derivative of both sides with respect to x. And the derivative of x is 1, and the derivative of sine y is going to be the derivative of the outside, keep the inside, times the derivative of the inside. I'm going to solve for dy dx and get dy dx equals 1 over cosine y. And then I'm going to say, well, I really want this to be in terms of sine y so that I can then put it in terms of x. Well, if I go back to the top, sine squared plus cos squared equals 1. So if I rearrange this to make it cosine equals, it would be cos theta equals plus or minus the square root of 1 minus sine squared. So what we're going to do is we're going to restrict the domain so as only to use the positive value there. So I have 1 over cosine y can be rewritten as 1 over the square root of 1 minus sine squared y. Again, I'm not doing the plus or minus, I'm just doing the positive. I'll explain why in a second. And that's going to make this 1 over the square root of 1 minus x squared. There's the derivative of inverse sine x. Now, why did I ignore that negative? We took the square root, we had to put a plus or minus on it. Why did I ignore the negative? Well, the reason I ignore the negative is those inverse trig functions have restricted domains. And so if I have that restricted domain and I really look at that inverse sine function, let me get there in a second when my calculator loads up. Come on. I'm going to pause so you don't have to wait. In the second where I paused there, what I did is I put inverse sine x into my calculator. I set my window to a nice appropriate window here. And now if I look at the graph of inverse sine x, look at it. It's always going up. Inverse sine is a function that's always increasing, therefore its derivative should always be positive, therefore I ignore the negative on the square root. So that's why instead of plus or minus on the bottom, I just put plus square root 1, 1 minus x squared. All right, so now, as I said before, really you just need to memorize all this. Now the nice thing is there's 6 things here, but you really need to only memorize 3. The derivative of inverse sine u is 1 over the square root of 1 minus u squared du dx. In other words, 1 over the square root of 1 minus the end part squared times the derivative of the end part. Now often what I'll do when I'm describing this derivative is I actually just write it as du. Nope, not dy. Let me fix that. When I take the derivative here, I usually just write it as du over the square root of 1 minus u squared. The derivative of the end over the square root of 1 minus the end squared. The derivative of inverse tan u is du over 1 plus u squared. And the derivative of inverse secant is 1 over the absolute value of u times the square root of u squared minus 1 times du dx. This is the hardest one to remember, but also the rarest one to come across. So don't worry about this one as much. You need to memorize it, but if you're panicking, in the scheme of things, this is less important than the other 2. Well, that's only 3 derivatives. Look at the bottom row. Here's the derivative of sine, inverse sine. Here's the derivative of inverse cosine. 1, negative 1, 1, negative 1, 1. The co-functions just have the negation of the regular function's derivative. Sine, cosine, positive 1, negative 1. Tan, cotan, positive 1, negative 1. All right? So there you go. Let's do a couple practice on the back and we're good to go. So if I want to take the derivative of inverse sine 3x squared, I'm going to use that du, sorry this keeps tailing off, du over the square root of 1 minus u squared. So the derivative of inverse sine 3x squared is the derivative of the end, 6x, over the square root of 1 minus the end squared. So my derivative, f prime, is going to be 6x over the square root of 1 minus 9x to the 4th. If I have x inverse tan 2x, I'm going to need a product rule. So dy dx is going to be the first times the derivative of the second. The derivative of inverse tan is du over 1 plus u squared. So it's going to be the derivative of 2x, which is 2, over 1 plus 2x squared. So there's the first times the derivative of the second, plus the second times the derivative of the first, which is 1. So my derivative is 2x over 1 plus 4x squared plus inverse tan 2x. And there's my other derivative. And last but not least, find an equation of the line tangent to y equals inverse secant x squared at the point 1, 0. So if I need a tangent line, I need a point, I need a slope. To get a slope, I need a derivative. So the derivative of this guy is going to be dy dx. The derivative of inverse secant is du over the absolute value of u times the square root of u squared minus 1. So in this case, it's going to be 2x over the absolute value of x squared times the square root of x squared squared minus 1. So dy dx is going to be 2x over x squared times the square root of x to the 4th minus 1. Now, if you want, you have a couple options here as far as writing the derivative. You can write the derivative like this and walk away. But Mrs. Bibber, what about the absolute value? Well, what of it? Absolute value just takes something that's negative and makes it positive. Is x squared ever going to be negative? No. So the absolute value is really redundant. Now, let's say you really wanted to cancel these x's. If you were to cancel these x's, actually something would go wrong here because this should be able to be both positive and negative on the top. So if I cancel these negatives, what end up happening is you have to ignore the absolute value and write this as x to the 4th minus 1. This guy cancels with that guy, and you have 2 over x times the square root of x to the 4th minus 1. The absolute value disappears to allow for the positives and negatives. If you don't want to worry about simplifying at all, you could always leave it like this. But I just wanted you to be aware of the fact that the absolute value will drop off if you have a squared on the bottom or an even exponent on the bottom. But I digress here. We've got my derivative. I need the derivative at the point 1, 0. So at the point 1, 0, this derivative is 2 over 1 times the square root of 1 minus 1, which is going to be, well, wait a minute. If I go to take the derivative here, don't I end up with 2 over 0? Wait a minute, my derivative's undefined. Oh, but I know what to do with that. If I have an undefined derivative, that means the slope is undefined. And if the slope is undefined, that means I have a vertical line. And a vertical line is an x equals line. And x equals 1. So there's my line tangent to inverse secant at the point 1, 0. Since I have my calculator up, I'm going to bring it up just to show you what that looks like. So if I go into here and I do inverse secant, here's a weird thing that I do want to talk about, so I'm glad I'm putting it on the calculator. Do you see an inverse secant button? No, neither do I. Here's a silly rule that you may not know about inverse trig functions. So I have cosine x, and cosine x is equal to 1 over secant x. In other words, I take the reciprocal of the ratio you get from cosine, okay? Well, in inverses, the ratio is here. The hypotenuse over adjacent is here. And when I take the inverse secant, I get the angle. The original inverse trig, cosine equals 1 over secant, secant equals 1 over cosine, however you write it, means that you take the original angle and then take the reciprocal of the ratio. When I'm taking the inverse secant of x is equal to inverse cosine 1 over x. The ratio gets its reciprocal taken, not the angle. I don't do 1 over inverse cos, I do the inverse cos of 1 over x. So the reason I tell that story is because now we're going to come back here to the calculator. So if I want to do inverse secant of x squared, I need to do inverse cosine of 1 over x squared. Okay, so I do that. I'm going to go back to my window here. I need to change it a little bit. My x value is -3 to 3 is fine. My y values are going to become, come on, -2 to 2. I need them to actually be bigger because if you think about the restricted domain, cosine goes from 0 to pi. So my y values need to go as high as pi. So I'm just going to go from -2 to 4 just to get it high enough. And here's my function. And if I'm at the point 1, 0, which is here, I have a vertical tangent line. And that's the line x equals 1. All right, there you go. There's inverse trig derivatives. Woohoo! Not so bad. 13 minutes, under 15. I did that well for you. I will see you guys in class soon enough. I hope you followed along. Just memorize those 6 inverse trig derivatives, and you are good to go. See you later.